Okay, so good afternoon, everybody. Today we have the pleasure of hosting Professor Narayanan from Penn State University and also one of the directors of the Center of Brain-Inspired Computing. Vijay is the Robert Noll Chair of Computer Science and Engineering at Penn State University. He politely asked me to keep his bio short because I honestly, even though I know it all by hand as he was my PhD co-supervisor, it's very hard to actually read the full bio because it keeps updating with new accolades and new awards and new accomplishments every year. So I'm just going to state the most maybe recent ones. Vijay is a recipient of the 2021 IEEE Computer Society Edward McCluskey Technical Achievement Award. And of course, Vijay works on a lot of areas, ranging from systems to circuits to architectures, and in the last multiple years on the topic of today's talk, which is focused on bio-inspired vision. And I know a lot of you guys are working on vision-based applications and research at NEOS. So let me just conclude by saying that Vijay is an ACM fellow, an IEEE fellow, and also a member of the National Academy of Inventors. And today we will talk about distributed visual analytics. And I am being interested in not losing any time. Vijay, the floor is yours.
Thank you, Yasu. That's the only word Theo and Chris taught me. So they said use it everywhere. So I hope it was appropriate. Mask. I'm online, but that's okay. Unless they have anyone having difficulty hearing me. This is how I lecture in all places, just to make sure. I've been traveling a lot, want to be safe with everyone around. So if you want to see my face remotely, here it is, okay? This talk is going to be not on the bio-inspired aspect, so I moved on to beyond bio-inspired. So this talk is more stochastic and machine learning more than bio-inspired. So if you look at visual sources, I don't call this just as video sources. I talk about visual sources. The amount of data that's being generated by videos actually unimaginable. So if you really look at 2025, you can basically look at that number, 436 exabytes of data. I don't even know how many zeros are there in exabytes. It's that much, right? So, which means we are going to have a great difficulty in storing all the data that we are generating, right? If we cannot even store all the data that we generate, processing is even going to be difficult. So if you look at some of the roadmaps of the semiconductor industry and Semiconductor Research Corporation, one of the challenges that we are going to run is we are going to have far fewer bits available to store than the amount of data that's generated. So we need radically new things. And if you really look at the sensing mechanisms, they are going beyond your HD. They are looking at LiDAR data, 3D data, 3D cloud points. And if you look at other sorts of applications and medicine, you basically have genomics, you have biomics, you have all these proteins that are being generated. So the amount of data is really huge. So this essentially involves design issues that need to reduce amount of data that's moved within a chip from the memory to the compute, data that's moved from the edge to the cloud devices, which means empowering edge devices with some intelligence, empowering techniques like processing in memory, processing in storage techniques. So in today's talk, I'm going to give you a sampling of both. The first part of it is going to be focused on reducing the communication of data from an edge to a server, especially in these collaborative IoT environments, specifically because Kiosk is working a lot on a lot of those edge intelligence, right? So that would be my first part of the focus. And given that there are computer architects like Chris and maybe others that I'm not as familiar with, my second part of the talk will be looking at how would we make innovations in processor architectures to be able to support computing close to the memory. So that's kind of what this talk is going to be about. Before that, I just want to give you a quick catch up. And I actually picked 2007 out here because I believe that's the year that Chris actually finished. Theo finished a couple of years back. So just to kind of give you, we have been continuing to work on many of these image sensing aspects of it. Our initial work back in 2007 used to work on these tiny smart cameras that were actually looking at monitoring shoppers, looking at their reaction, what are they buying, or if they come with a child, what do they get? They come alone, what would they get? That research actually showed some very interesting things. For example, when people buy milk for the kid, they also tend to buy beer, right? So not very intuitive, but if you're a parent with a small child, you probably know why those things are true. And that basically led to analytics of where they place stuff in the stores, right? Moving ahead, we actually built a lot of these bio-inspired type systems. So one of our early systems was essentially showing the power of brain-inspired computing. So what you see in this chart, you can basically see this red blob and the blue blob, right? So the red blob was basically solutions that were traditional neural network type stuff. And the blue bar was essentially the bio-inspired algorithms. And the red parts were implemented on GPUs at that time. And the left part was implemented on customized FPGAs. And here the x-axis basically shows the energy was 2 to 3 orders lesser than the traditional algorithms running on GPUs, while the y-axis basically shows their accuracy on different workloads was really the same. I'll kind of jump to something more recent later in my talk. Now we have deployments of cameras in the wild, so as to speak, not to track large things, but tiny insects to look at pollinator diversity in this case. And here is a project that I could basically talk about the entire hour, but I'm not. But I just want to give you another example of embedded vision systems that we actually build. These are assistive vision systems, which basically assist visually impaired people to go and grab things. Try and see whether this video plays, probably will.
Lucky Charms. Scanning. Please slowly move the camera in front of you. I'll tell you when I find the item. Scanning. Item found. Click the guide button when you are ready. Guide button. Guide button. Started guidance. Lucky Charms is 31.1 inches away, 34 degrees to the right and 11.7 inches below from the camera view. Right, right, right. Left, 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 left. Lucky Charms is in front of the camera. Click the confirm button or shake the phone when you are ready. Guide. Confirm button. Please move the item in front of the camera. You got it. You have Lucky Charms. You can go back to the select.
So this actually looks pretty simple, and I think maybe some of you guys may have seen this earlier. But the biggest challenge in these type of things, when you see it visually, it looks very easy to pick an object, right? What typically happens is, let's say you see this remote, right? I'm placing it here. Even if I kind of locate this, my arm and hand needs to go and pick this up. So what typically happens is if I don't see it, even if I'm guided here, instead of grabbing this, I may grab this. And she may not like me grabbing this, right? Instead of this, because it may, it's just a few inches away. And one of the pain points, while now this works very well, it really took about 6 years to get it to pick things every time. And again, we started with a lot of fancy things. We started with Google Glasses. We started with the Microsoft HoloLens. We tried everything. But then many things need to actually try and converge. First is it needs to be cost effective. It needs to be something people will be willing to use. It needs to be accurate. So eventually when this latest iPhone 11s came, they are no longer the latest, but when the iPhone 11 came, they basically had these LiDAR sensors, which basically had some depth estimation. And once we were able to use a very simple idea that if someone basically keeps the phone on the hand, then you can basically use the depth sensor from the hand to whatever object that you need. Now, your phone is a proxy for your hand. So now with the LiDAR sensor, you could basically locate exactly until you go and pick the object. And I cannot imagine over the 4 or 5 years, how many times we basically had these type of trials that were done. People would go up here and then navigate further away, like 1-inch problem. And that 1-inch problem is actually very important now in automotive setting, right? So especially when you're trying to park very closely, or if you want any of these cars to actually drive in real scenarios. When I say real scenarios, I'm probably thinking about if you need a car to drive somewhere like Ledra Street, right here, right? So where it's very crowded, not just empty. So the few inches can make a difference between whether I can really drive or I'm just going to stop. Like me, when I'm driving in such a new city, there are too many people, so I'm kind of stopping. So those type of things can be avoided by this distance stuff. And I'll kind of point out other
Lucky
things that we are
charms.
doing. So here are other type of systems that we are working on. One is actually on smart manufacturing. So this is actually, I know that there is a student from Texas A&M. This is actually a collaboration with Texas A&M, the industrial engineering department down there. So the goal here is to basically have legacy machines. You need to be able to predict their failure or predictive maintenance. However, they don't have all these fancy sensors to be able to do these things. So what we really do is we retrofit some of these legacy machines with sensors like vibration sensors and thermal sensors. And we basically leverage the vibrations and thermal differences as an energy harvesting mechanism as well, while doing the analytics at the edge. And on the right side, you basically see this prototype. This is one of the first non-lethal insect monitors that actually work in real world. So they're basically looking at a live camera, looking at the live behavior of insects. And by the definition of insects, you know, they're really, really tiny, right? So to be able to have classification and counting of them is tough. And more importantly, these things need to be deployed for 2 to 3 months with no attention to these things. And it doesn't really have a power socket to go and fit in somewhere. So we basically have a solar panel. So this is also a self-powered system. It's been both in Oregon in a farm as well as in the Penn State Arboretum for 2 stints of about 3 months. And there's a ton of new data and relationships that we are finding out between pollution, weather, insect behavior. And the reason I point out some of these systems, it's very good to go back and get a good accuracy in ImageNet or do some challenge. But when you deploy the real system, it's a whole new thing. For example, you will basically have glare. You will basically have some rain and mud stick on some of the encasings, right? So how do you make the system work in all these type of things? And if you're further interested, you can see about a 6-7 minute video at that YouTube link later on. So today I'm also going to kind of not talk about all the technology aspects of it. So the technology aspects that we are going to look at in this talk is essentially bring data and processing closer together. One of the aspects that I'm going to be talking about is monolithic 3D integration. And this topic is probably close to Chris's heart, because when Chris was working on his PhD in 2005, he was basically working on stacked 3D processors. And the key difference between stacked 3D processors, which you probably get some variants of it in your cell phones, like 2.5D technology, is in earlier technologies, you can basically think about it as a large wafer stacked on top of another wafer, and you can kind of think you drill holes to make connections to it. And those connections were called as through silicon vias. But those vias were pretty large. So when I say large, you could probably fit about 10,000 to 20,000 transistors in the size of a via, right? Based on how big. But in this monolithic 3D, it is basically like you have one layer and then you make another layer right on top of it. So the connections are very fine grained, right? So the connections don't take too much space. That's the key difference in monolithic 3D process. We also try and, when we do this monolithic 3D process, we also integrate volatile and non-volatile elements down here. So we'll probably talk a few of them out here, but the key part is my group's technology focus is on trying to find out ways in which memory and compute can be close together. So that kind of sets the overview of what's happening in the group. So I'm pretty certain all of you came for the distributed analytics part out here. So let's jump into the distributed analytics part. So the first part that I'm going to talk to you about is the notion. I'm just looking around to see how many cameras are here. 1, 2, are they cameras, right? They are. 1, 2, 3, 4. So let's think about these 4 cameras all looking at one person, right? So let's say they're all looking at Christos. So there are many views. How many views do I need to kind of say whether it's Christos or not, right? So the whole notion out here is if we have multiple distinctive views, it's probably adding incremental accuracies. But if I use all those views, it's basically consuming bandwidth, it's consuming power consumption at each one of these sensors. So one of the first explorations that we did is to try and answer the question, which information is important for recognition? That's kind of a challenging task, right? So if I knew which information is important, then I could basically turn off other aspects of it. And one of the aspects that we basically tapped in was essentially a lot of these models today are not those bio-inspired models, but they are trained models, right? Like in deep neural networks. And in a trained model, you're essentially already training the model such that you're trying to increase the likelihood that whatever is detected is tending towards the data set, and which means you have a low entropy. That's really what you're doing in the training part. So we landed up using this entropy as a proxy of a metric of the usefulness of a particular view. So if the entropy is very low, you know that whatever you're observing is somewhat related to what you're trying to classify. So it basically says it's adding some value towards my task of classifying something. If it is far away from whatever you're trying to do, it's probably saying it's not going to give you any information with respect to the trained model, right? So that's really the key intuition out here in this case. So what we landed up trying to do in this particular case is we have a bunch of cameras that are looking at different viewpoints. And for some of the cameras that are gaining views at a very similar angle, we basically kind of just aggregate those features together. And then if you look at this part, we are essentially applying this entropy-based likelihood estimation to try and check whether the contribution of this camera cluster is valuable enough in the collective decision it's going to make. But of course, because of that, our network has one small part that's running in on the edge devices, and it basically has the combined centralized view from all the cameras in the backend. And the part that we are focusing on reducing is each one of these cameras having to transmit its data to a central server, right? So at the cost of small compute to do the likelihood estimation, we land up avoiding to transmit data from those cameras that don't essentially contribute significantly to this accuracy. Of course, this is a trade-off, right? So I can basically turn off everything, which means you don't make any classification. If you pick the right ones, you land up doing. So the trade-off really depends on, for this entropy likelihood estimation, you choose what is the threshold. And when tuning this, what we land up seeing is we could decrease the communication energy cost by about 3x, which is pretty substantial. Whether my lens works like some of my mobile cameras, whether they work for 20 minutes or 1 hour, it's a huge difference from the power perspective. And in many cases, the communication is a significant bottleneck in these scenarios. Another thing that's actually happening in this particular task, we also land up doing a weighted view pooling. What does weighted view pooling mean? So let's say I'm looking at one view which is looking at your frontal face, right? Other view which is looking at your side. So let's say I look at Chris right now, or maybe I look at myself. There is a mask. So I'm not really seeing as many features that I like to see. So I'm probably going to weigh that feature a little more. And maybe your side view has less of a mask, so I can see you more. So I would probably weigh it more. So it can basically dynamically adapt itself to these type of perturbations. And one of the things that we saw in this case is because of this weighted pooling, it was pretty robust towards failures or occlusions in different views in this particular case. A corollary to this problem. So the first problem that I actually talked to you about was the camera looking at the same viewpoint, right? So we just talked about whether it's going to transmit that feature or not to the centralized stuff. You can also asked this question: if I look at this viewpoint, should I send the features in high resolution? Should I send it in lower resolution? Or, of course, not send it at all. So in this particular follow-up work, we went from 3x reduction to 5x reduction, albeit at a cost of a 2% accuracy loss. What we land up also making a decision here, we use these weights above the threshold to determine the resolution at which I need to send the image, right? So now you use a lower resolution for something that's not as important, a higher resolution for something that's very important, and something below a very low threshold, you don't even send things up. And when you basically just send a low resolution image and then basically do sampling again to restore that image, it doesn't get you within the 2% accuracy. There, the accuracy loss could be like 5%. So one other trick that we landed up doing is we basically applied a learned super resolution at the server when it was basically getting things. And just to give you a gist of what learned super resolution means, if I see a lot of images, right, then you can learn to fill in certain portions of it to recreate the super resolution image. So that was the learned super resolution technique. So one of the things that's becoming important is just not multiple cameras looking at the same viewpoint, but things like that. There are specifically defense analytics uses. One system that's very famous is the Argus defense aircrafts, where you basically have multiple cameras that are kind of pieced together. In fact, the system that was built then was basically multiple iPhone-like cameras, but an array of 64 by 64 cameras that were then capturing a city-wide view with a bunch of cameras, right? So now the whole goal here is you're essentially recreating a large area high-resolution image by fusing together a bunch of independent sensors. And the view that you are seeing here is the view of the 4th largest stadium in the world. Does anyone want to guess where it is? Pretty unlikely place. It's in State College, which is the home for Penn State University. It probably has a population of about 50,000, right? So, but that's this stadium out here, and we basically look at drones basically capturing different sections of these cameras. So now in this particular type of scenario, the amount of data that needs to be transmitted is pretty huge to any centralized server. And imagine there are 110,000 spectators clogging into a wireless network, which typically serves 50,000 people. And then if you also want to add these type of drones that are basically clogging that network, communication bandwidth is a real challenge, right? So if I can get to analyzing those scenes with the same accuracy, that's actually a major win. And in this particular case, what we landed up trying to do is we started applying this likelihood now to these different patches, and then use the attention scores from those patches to kind of recognize the entire scene. And one distinct aspect that we landed up seeing here, compared to some of these hierarchical resolution techniques or other techniques, our technique was able to identify tiny objects in each one of these patches, as well as scenes that were correlated across these patches. And of course, playing around with the threshold, you can play around with the desired accuracy and the amount of communication and amount of computation that needs to be done on the server. So that's kind of the trade-off out here. So my theme here has all been on one very specific aspect, which basically says calculate the entropy as a metric to determine whether certain views are important, be it in a view that's getting a single point or trying to fuse multiple views to get a much larger perspective. One of the things that I want to kind of point out while I actually showed this attention-based metric, we also applied, and that's probably the closest correlation to Theo's advertisement of biological part that we have. We also use the visual attention mechanism called saliency as another metric. And that's really how the human eye typically works. Saliency metric is basically center is different from the surround, right? So, for example, one of the saliency metrics is orientation. On a hot day like this, some of you or most of you are like this because you want to listen to my talk. Some of you are tired, so your orientation goes this way, right? So if you are the only person sleeping with many people awake, you stand out. But if everyone is this way and you're the only one awake, you stand out again, right? So that's the metric of saliency. And when we tried this saliency metric, it was not as good in the qualitative results that we got as compared to entropy. And that's not surprising, primarily because these are learned models, right? So it has already learned a lot of data. It's just not extracting top-down attention as in saliency. So now I'm going to move on to kind of the depth estimation part, which I said was pretty close to me. And this really stems from all things that I've been talking about are visual space, right? In the vision space. One of the key challenges with vision, of course, the first question that you would get when you work with any of these autonomous navigation vehicles, should I not drive in the night, right? So low lighting conditions bad. But one of the earlier problems that we landed up facing, even for these persons with visual impairment, was if there is a glare from the light, it basically obscures everything that you see, right? So underexposure or overexposure, both are challenging. So the first approach that we took to this particular scenario was actually take up the challenge. What if I'm not going to take any RGB data at all? I'm going to just sample the LiDAR-based depth. And when you use LiDAR-based depth, the problem with every LiDAR sensor today is they are much sparser in their sampling than RGB type resolution that you will end up getting. So I'm not sure how well this shows up as sparse. So you basically see a bunch of distinct dots. So our goal was basically to derive a depth dense from sparse dense, from sparse depth. So if you can use a normal LiDAR and then do a learned reconstruction to a dense depth. And key aspects for this was basically a GAN-like architecture, which used an attention module to kind of extract the specific objects and kind of make them pretty uniform across the spatial scale. And we also had these residual connections that helped to balance between what was already extracted and what new information could be augmented in this particular block. So maybe this picture kind of demonstrates more than the algorithm. So what you're really seeing here is the depth information across different parts. So you can basically see the ground truth in this column. And this is what I mean by sparse. And these three are prior techniques that essentially require a fusion of RGB and the sparse depth, right? So these were all based on the notion that you had some RGB data. And our work was one of the first. The reason I say one of the first is I can't validate that no one else has done it, but a peer-reviewed paper claimed this was the first, right? So here is one of the first approaches that basically did not use any RGB data, but still went from sparse to dense depth. And you can basically see that because of this aspect, the data volume, you can see the last row in this particular case, our data volume is significantly lower than any of the other techniques because we don't need to feed the high resolution RGB image. And more importantly, in scenarios where the RGB image is not available, like in a dark light on over part, we can still estimate the depth very well. And if you imagine, why would I even be worried about dense depth when I have the sparse depth? Think about some of these protruding objects with a different shape, right? So that could make a difference between whether your vehicle will go under an underpass or will it hit that, or would there be a projection that's going to hit the parking lot kiosk. And in fact, when I was driving and there was someone who was having difficulty getting into this parking lot. So those type of things are pretty important. So one of the other things that we did is because we already were doing very well compared to things that were fusing RGB, we started thinking, if we have RGB, would I just take the approach that previous people did? Am I going to take RGB, LiDAR, and then fuse them together? No, we basically thought we will do something different. If we have the RGB image, then we will basically do simple things like the SIFT features, right? And what the SIFT features will do, they are not trained features, they are traditional computer vision techniques, right? SIFT features give me, I think Christos probably did a lot with SIFT features, right? So it basically tells you where the edges are. And you know where the edges are is really where you're going to see depth differences, right? So rather than sample everywhere for the depth information, I'm going to sample where there are prominent edges in the RGB space and direct my LiDAR there, because the LiDAR is doing slower number of samples, fewer number of samples, rather than doing uniform across. We basically do uniform for specific regions. And that's really what we land up doing. So if you look at the RGB part, these are sample SIFT features that you get from the RGB space. You feed this into the LiDAR and do this directed sparse in this particular case. The W equal to 2 basically says we are weighting the locations where there are salient points from the visual extraction more than the rest of the points, but we are sampling exactly the same number of points. We just choose to sample differently in this case with the guidance and then do the dense depth. And in this particular scenario, again, one of the things that you land up seeing is we land up getting about the same accuracy with also a significant reduction in the size of these networks. So we are pretty competitive with all these RGB techniques, with an additional benefit because we are doing this directed sampling. Many of the samples obtained are clustered together. So the entropy of the sample data points are much smaller, which means they are much better compressible. And when you start thinking about sending things back to the back end, there's an additional saving for the same quality that you'll end up getting in these directed LiDAR sensing, as opposed to just simultaneous LiDAR and RGB sensing. And more recently, we have actually been looking at, sometimes you have, when you're driving, which probably doesn't happen here that often, let's say you start getting snow flurries, then your LiDAR sensor is going to be messed up. Let's say you have going into a tunnel with no lights on, your RGB sensor is off, right? So which sensor is better needs to be dynamically decided as opposed to statically decided. So a new technique that we are working on, which is actually going to be presented in ACM Multimedia in 2 months from now, really looks at a model which is able to weigh in the importance of the RGB versus the LiDAR. And if any one of those fail, it's still using the same network and basically just changing the weighting to be able to do the inference. And again, this is in the same theme that I started with in fusing multiple cameras, but this is about fusing multiple modalities together in terms of failures. And here is what's happening. So you have the RGB input and the sparse input, and you have these conditions where you may have no input from the RGB or the LiDAR data, right? And you can basically see prior works essentially kind of are not up to the mark with the ground truth when some of these modalities fail. And in our technique, we basically is called as the fusion GAN, which is basically fusing both of these things. And we basically did this robustness aspect by weighing in the and training the network for these failure mechanisms. And you can see they replicate the data even in the absence of one of these modalities dynamically. And that's kind of what is important in these type of scenarios. So one of the things that we have been working on is actually then plugging and playing many of these visual pipelines that we have and looking at what is the challenge, right? I've been kind of emphasizing communication as the challenge, right? But when you start placing these things across a typical system, you have many challenges. So we have many of these end-to-end pipelines that have been characterized on where it is spending the time in a system. And in many cases, at each and every node, a significant amount of time is actually spent in shuttling the data from the memory down to the processor, right? So now, earlier I gave you a system level view, but now if you take a node level view, where is the time being spent, right? And the data movement within a node is 200x more costly when you move it from the memory as opposed to be it in the local register, right? So that is a problem that we have been working on. And I'll probably want to just give you a sample of this particular techniques rather than go deeper so that I have some more time for taking questions. When you start thinking about doing computation close to the memory, you can land up doing this on your on-chip SRAM. So if you really look at the last level caches in a processor, that's pretty substantial, right? So you can have caches that are 40 MB or 50 MB caches that could be the last level cache. So one of the things that we have been working on, this is work with the Intel researchers. We have been modifying their cache architectures to include computational support in the caches. And the key to our difference of doing computation in the caches, unlike prior works, was to use a very simple notion: memory and compute could be universally interchangeable. And that universal block is a lookup table, right? In simpler words, it's a cheat sheet, right? So you basically, for example, if you want to do multiplication, 4 times 1, 4 times 2, 4 times 3, 4 times 4, before you go into the exam room, just write it down: 4, 8, 12, 16, whatever. So even if you're weak in multiplication, if you can know how to count, you can see this. but that's a lookup table. What I showed it to you for multiplication, you could do this for other functions, sine, tan, hyperbolic, many of these functions. And of course, you could approximate these things using things like Taylor series expansion for accuracy versus number of entries data, right? So again, if you think of, hey, if you're not familiar with these lookup table techniques, you're still worried and bothered about my solution, right? How will I place all multiplication tables in a finite amount of memory? That's really where these approximations work. So for example, you don't need to store everything. You could basically do a simple shift for multiplication by 2 in a binary system, right? You could add things again and again. So what we'll end up doing in this particular structure is we have these yellow parts that you can see very tiny, right? There is a blow-up chart later on, which I can show you. These are these entries that are these lookup table entries. And you see this very small box called as BCE. That's where you support very simple operations like adds and shifts. Together, they actually land up doing a lot of these deep neural networks and get you about 100x faster than contemporary GPUs, right? So that's, again, the real reason for the power comes from a lot of parallelism in the memory compared to the CPUs, or for that matter, even compared to the GPUs. That's where the speed up comes from. We have been working with Micron in trying to integrate embedded processors within the DIMM slots of DRAM. So this is basically now within the DRAM banks, you basically start computing without having to go through the DDR3 interfaces, which is a significant bottleneck in terms of bandwidth to go to the compute, right? So this type of stuff in our evaluation landed up seeing about 200x benefit. Another major type of technology, which many of you may have come across, are these cross-point architectures. Cross-point architectures are, as you see, more like vertical and horizontal wires, where you basically see a connection between them, but that connection is basically a programmable resistance. That programmable resistance can essentially store things like your synaptic weights of a convolutional neural network, right? And by basically summing the currents across these weights, you can do matrix multiplication, sparse matrix multiplication, things like that. And given that these memories, as you can see, are just two terminals, they're just like wires, you can essentially end up seeing significant density advantages compared to other technologies. We get 500 to 200x. I think I'm not going to be able to spend more time on the last part, which is most recent work that we have been doing. Of course, the holy grail for storage is flash, right? So when you start landing up getting the SSD, so for example, I think the USB that I just gave her was an 8 GB, which fit into my pocket. Of course, these days you probably get a 1 terabyte storage that would fit in my pocket, or even a 3 terabyte. And that's basically an SSD, right? Now, if I can basically start doing compute either near the SSD or within the SSD, when I was talking today, right, it could have basically processed the week-long videos that I actually took and basically have updated all these detection in how many times was Theo showing me you're out of time in the 5 talks that I've given this week, right? Would have actually given me those results right here. And it would have done this without draining my battery. It could have done this in a way that it basically scans stuff. And that probably needs to wait for another day for you to see this. I'll try and see whether I have a video of that to kind of finish that part. So what you're seeing here is actually a very similar scenario to what I was talking about. So these are all videos. When the videos or images were stored, they basically did some metadata extraction to say what objects were there. And you're seeing someone telnet into this because they are doing the telnet to this SSD from their desktop server. And what this is actually doing an analysis, it says frame 1 has a giraffe, frame 2 has a giraffe, it's giving the bounding boxes. And then our task here is to find out, is there a person feeding an animal, right? For that to happen, it needed to have both a person, a giraffe, and food, here in this case, lettuce, right? In a typical system, what would have happened is all my video here would have gone to a server or some other compute platform, did that computation. But don't think this is my phone, think of this as my storage, right? Now, what would have happened is it's just scanning all this compute with the FPGA that was very close to this SSD, filtering out all the data. It basically found out only 1 in 3 of these frames actually had something to do with this video. It's sending that downstream for further analysis, looking at relationships or other things. So it basically reduces the amount of data, right? And we have seen 10 to 12x type reduction in this data. But we are not stopping here, right? So in this particular case, this is a system with an FPGA close to an SSD. The bandwidth between the SSD and the FPGA is already much higher than a PCIe interface or an NVMe interface that you basically have. But now imagine, similar to my SRAM, if I land up doing compute in the NAND flash chips, that will be extraordinary. But one major bottleneck that I have right now, if you store more than 10 to the power 4 times onto the NAND flash, I have to throw my NAND flash. Luckily, when we store videos, we basically store them once and never see them, right? So for example, some pictures that I took from my previous trip from Cyprus, I probably saw them again during this trip and maybe once between the previous one, just to kind of reminisce. So you don't write 10 to the power 4. Flashes were not made for that technology. But if you do compute, intermediate results will be about 10 to the power 6. Even when you run AlexNet or GoogleNet, after one analysis, I can throw off my flash device. It's not going to work. So newer technologies with more endurance are required. And that's something that we are looking at to make that possible. Thank you. And I'll take any questions.
And we do have time for a few questions, and given of the work that Vijay just talked and the work that we do at GEOS and especially the UAV team with the first few things that Vijay showed, I'm pretty sure there should be a few questions. So what I would like to, if possible, use the microphone that's next to your seat so that the people that are watching us online and hear us. And if there are any questions online, you guys can raise your hand and Katarina will let me know and introduce you.
Yeah, and this is a picture of my academic and real family. They are also sitting down here, so I would like to thank all of them. My students for bearing with me and my family for bearing with me missing in action. So both ways. Thank you.
Questions? You don't ask questions, then if you have that, ask good questions. Yes, I did.
Hello, that was a very nice presentation. So you mentioned about multi-view camera systems, and so I have two questions. So it looks more like engineering the data set itself to have like better samples that would contribute more to the information for whatever classification we want to do. So how closely do you think is it related to the idea of data-centric AI? And the second question is, so we don't really have such data sets available. We have like only data sets like, for example, ImageNet, if you're talking about classification, or Cipher10. Do you think would it be possible to formulate a problem where we are looking at an object of interest from one view and predict the other view? For example, look at the right side and be able to predict the left side, or look at the front and be able to produce the back side.
So let
Thank you.
me kind of repeat your questions first for the purpose of remote audience, just in case. The first question really pertains is how do you even get the data in realistic settings? How did we land up doing it? What is there? So the data set that we used was from a collaborator, Laurent E.T. at USC. So that data set basically has data from 8 different views, and basically how he generates the data is basically he has miniature version of many of these objects. He places this in a turntable, basically rotates this turntable with different lighting conditions and other stuff, so that data set is available. We also have another data set which is actually at the other extreme, so it has basically 80 cameras views that are there for these type of objects. And we are also creating a new data set for these insect data sets that I basically talked to you. Not just a 180-degree view, we are also trying to see how we could kind of project it in a 360-degree view, because if you see an insect on the top as opposed to its bottom, it's very different, right? So you may just see and maybe all insects look, this is not a statement because I don't know enough about insects yet. They may look the same at the bottom, but they may be very different at the top based on their colors, right? So the data set that exists right now is referred to in this work that we have done. So you can actually look at it, it's publicly downloadable. As far as the newer data set for the insects, maybe within the next 6 months to a year, that would become available as well. And the second part of your question, I believe, is a corollary to the first part. So once you have these views, you could basically look at 2 different aspects. So a lot of things that I actually showed you right now are more of bottom-up attention, right? So it's basically looking at how well this particular view fits into the model training, the lower entropy, but it has no notion of higher level knowledge, right? So you could basically start then thinking about additional attention mechanisms that are coming in from learned storage, right? So what I mean by learned storage, it's like knowledge representation farms, right? So if you know, for example, insect is related to a leaf. So if I find a leaf, I should find it harder to find an insect in this particular location, right? Or if I know an insect can camouflage in a particular color in a leaf, I should basically start thinking about other ways in which to distinguish that stuff. So on this direction, what we are doing right now is you saw our work on fusing the RGB data and the LiDAR data. So one task, for example, that's very critical in generating these depth information is, let's say, I want to carry out some special operations in this particular room. I'll basically send one of your drones that you guys are really good, and I need to go around this room in the quickest possible time, get the samples, get out, because I don't want my drone to be taken out, right? Because it's doing this. In those particular scenarios, in addition to what it basically images, if you have some prior models of, oh, this is how a chair is going to look, this is how a vehicle is going to do. So it basically fills in parts that are not sampled with learned models, right? So model-based augmentation and knowing of this knowledge, a person is better recognizable by the front view than the side view, or maybe a higher level view. From tomorrow, in Cyprus, in indoors, people are going to start wearing masks, so kind of reduce that weight to the other stuff. That type of work has still not happened, so that's pretty active. So to try and fuse higher level knowledge into these decisions is an active area of research yet. I hope I answered both your questions. So this is Chris's turn to get back at me, because I used to trouble him for 5 years every day.
So you mentioned this notion of processing in memory, and you said you can have it, let's say, in SRAM, in your last level cache, you can have it in DRAM, and even in flash storage. I was going to ask, how does this mismatch in the density of the memory cells, let's say between SRAM, last level cache, and DRAM, how does that affect the decision of the type of processing element that has to be put inside this this memory?
So that's a hard question. I don't think anyone's actually answered this particular question, right? So it's hard enough to get memory companies to even consider putting in some processing, right? So even now, if you really look at the research side of these companies as opposed to product side of these companies, I don't think the product guys still believe the density should be compromised, right? So on the research side, I think in the DRAMs, again, they're making their fusions because of the density gains. So if you start putting in processing, so it's not like if you insert an Pentium or i10 core in to DRAM memory, you got your processing memory, right? So the whole challenge here is to get the granularity right without perturbing the density, without changing things. So the closest example that I can tell you based on my experience from a very practical deployment viewpoint, when we did this work, even for an SRAM cache, they were not willing to look at any modifications to those subarrays, because they wanted, that was already tuned, optimized, handcrafted for power, rail, density issues. However, with a bunch of subarrays, if you needed to add one very simple core, they were willing. And the granularity at which that you would do that in a DRAM basically increases from a subarray to a bank level, right? So that's kind of the freedom. And again, the core complexity goes from very simple arithmetic to maybe a stripped down RISC-V core that you can do. And I think UPMEM, which is from Europe, is probably a good example of one of those RISC-V-like processes integrated at the bank that's practical. I think there is a little more movement to first even believing that you can do this. Samsung came up, again, it's the research group of it that came with a prototype chip in IEDM last year and ISSCC, not IEDM, ISSCC. So the question of what is the granularity is, I think, a lot more commercial decision. How much of it will I sell? Who's going to use this compute capability? Who's not going to use this compute capability? Will they pay me this 2 cents more? And in a market which has 1 cent margin, that's a really tough question. So I really wish I could answer the question, but if I could answer the question, I'd probably be in some beach enjoying my life because I would have made so much money knowing that answer.
I have a couple of, well, actually I have one question in 2 parts. Okay? You mentioned a very good example, which is part of the work we do at the center, but it's more relevant. You mentioned about the drone going in and out and very quickly. A lot of our work comes from emergency response scenarios. So basically, you want to search and rescue, for example. And one of the things mentioned was about having multimodal sensors to make up for changes, rapid changes in the environment, which on the UAVs happens much more often than the car. For example, you can turn the camera, there's the sun immediately changes your luminance and more. And what you mentioned also with the demo that you showed, has anybody thought about using semantics? You recognize 2 or 3 objects with the multimodal sensors, and also integrate semantics where you can start using what's going on, and hopefully run it in some sort of real time without having to send the data to the cloud and back.
Yeah, I was almost intuitively thinking this was my laptop. I wanted to press an escape and open up another PowerPoint slide to show you that aspect of it. We have work called as DoubtNet that we did exactly for that particular reason. And that's very relevant to this picture that I showed you from multiple cameras looking at like the Beaver Stadium. So if you observe something in one camera, it biases the likelihood that this is what you may see in that camera. There is a downfall to it too. So if there is any surprise element in the other camera, you may miss it. But otherwise, you're kind of biasing. Hey, I saw Theo, so I must see Chris here, right? Or I saw Joe Biden, so I should see Kamala Harris. If so I'm pre-biasing my scenario. So that's exactly what we do. And the image that I have is kind of interesting. It's basically a dog playing with a circular object, right? And it's red in color. So my network basically says it's a dog and identifies this in a different view as an apple. But then when you see a dog, then this apple kind of biases itself. It's circular. What else is circular? Okay, this is a ball. And then what we landed up doing is we basically fused this object recognition pair with WordNet, which is basically giving you the semantic distance between the dog and the apple as opposed to the dog and the ball. So it basically figures out this is much closer, so you must be wrong. And of course, it also looks at, yes, the confusion between an apple and a ball is very high. Both are circular, both have red in color. So yes, so what we did there is basically we went into a more complex, deeper network if we had a doubt, right? So we use the semantics to kind of disambiguate that type of work. And there, again, we did not do this in the context of multiple cameras or fusing these cameras. We just did that in the context of a single camera, but just using the semantic information to decide how much effort that we should do into the classifying engine.
Okay, one other application we're looking at is actually traffic estimation. So basically, we have a lot of people working on this. They extract the visual pipeline and they try to model the traffic in terms of volume of cars per unit time and so on. And maybe that's another part where we do the semantics, the semantic relationship as well. Are there any? Oh.
I'm typing, yes. Is there anyone online, or did you all go to sleep?
I'm Adil available online, so I have a particular question.
Yes, Adil, go ahead.
It's about the sparse to dense part of your presentation when you were specifically talking about how you can get the depth images even with the related to the LiDAR. So what are the implications to apply such model on an onboard sensor or a onboard computer board which has a very limited computation, and we don't require RGB images to be coming out frequently and still be able to explore an indoor environment and map the object of our interest, especially for search and rescue purposes, what just Professor Theoharitis was asking about. So I was thinking, what are the implications, or how we can use this strategy for such similar applications?
Yeah, so Adil, if I can kind of repeat your question, you seem to indicate, are there opportunities for using the sparse to dense sensing in search and rescue operations? Was that your question?
Yes, exactly. So if we have a very limited computation only on board, not via server or doing on.
Yes. So if you notice, one of the focus for us was actually on transmission of the models themselves and the points that were obtained from the LiDAR data. We didn't focus as much on the computational cost of the models in this particular case. However, some of the model sizes that I actually showed you and the compute flops that were required for some of our models were relatively less than comparative models, especially because our data volume did not meet the RGB, right? So, however, we have not necessarily looked at getting the leanest model for sparse to dense in this case, because our milestone was actually for the first time to do sparse to dense without the RGB guidance. Your approach of can we get even to a smaller model? Maybe we can start using some of these student teacher networks to try and get even smaller networks that may be more suitable for the type of environments that you talk about. But having said that, I believe the platform that we have would fit into some of these small NVIDIA GPUs. So it really depends on what your embedded platform is. This is already suitable for some of the higher end embedded platforms. But if you are thinking like an Apple Watch or Arduino sensor, yes, it has too much compute. It wouldn't fit in there. But that's a research that is yet to be done. We haven't done that because even this work was just completed last year. So that may be something that you can look into.
Yes, thank you. That was my.
Okay, we have maybe time for one short question for afternoon. Okay, well, at this point, I would like to, on behalf of the center, thank Vijay, and of course, all of you guys for attending. If you have any questions, feel free to approach Vijay and ask him, knowing him many years, he'll be more than happy to chat with you as well as you want. Thank you, everybody. Thank you.
And thanks everyone for joining in. I'm pretty certain I'm going to trouble a few of you to learn more about your work over the next hour or so. Okay. And for people joining in remotely, thanks. And I do see Elena. Thanks for joining, Elena. Yes, seeing you again. Bye.
Thanks, Vijay.
And thank you to our technical support person here. Appreciate it.
Katerina.